Hello and welcome to this GeoStudio Tech Talk on coupling 3D stability and seepage analyses. I'm Catherine Dompierre and I work with the GeoStudio engineering team here at Sequent. Today's webinar will be approximately 40 minutes long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will be available so participants can view the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists, comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields, including stability analysis, the movement of water, contaminants, air, and energy through the ground, and stress and deformation in soil and rock. The integrated GeoStudio software suite enables you to combine multiple analyses using different products into a single modeling project. In today's webinar, we will discuss how to combine SLOPE3D and SEEP3D to evaluate the conditions of a heap leach pad. We will start with the background information on 2D and 3D stability analyses, as well as details on the heap leach pad project site. After reviewing the analysis details, including the steps for setting up the 3D geometry, SEEP3D and SLOPE3D analyses, we will then demonstrate these steps and review the results in GeoStudio. 2D slope stability analysis is typically more commonly used than 3D stability analysis, given its relative simplicity. And in many cases, a 2D analysis is adequate or even the best tool for analyzing stability of a given site. 2D analysis assumes that all deformations occur on the plane represented by your computer screen. This assumption is reasonable for many civil projects, particularly for linear infrastructure where the geometry is fairly constant over long distances like this roadway or this channel. 2D stability analyses often produce lower factor of safety values as there is no frictional resistance provided by the ends of the sliding mass. This typically leads to more conservative design when using 2D stability analysis, which in practice may be considered the desired approach. However, 3D analysis is required when the plane strain assumption is invalid. There are three main characteristics to consider. The first is variable topography, particularly narrow, steep slopes. The second is complex pore water pressure conditions that vary in 3 dimensions. And the third is geologic structures like weak plains or faults, which lead to translational, not rotational failures. When one or more of these conditions is present at a project site, a 3D analysis is typically required. The project site contains a heap leach pad associated with a copper mine in the Andes region of Peru. Heap leach pads are mining facilities where ore is placed in a pile on top of an impermeable base, which typically involves a geomembrane. A solvent is applied to the surface of the ore pile. Metal in the ore dissolves into the solvent as the solvent moves down through the pile. The solvent is then collected and removed for processing. This particular heap leach pad is located in a narrow valley with a liner system below the ore. After the metal is leached from the ore, the heap leach pad remained in place, given the limited space at the site. Given the variable topography and weak layer associated with the liner system, 3D analysis of the heap leach pad was necessary. Though this is not the exact heap leach pad assessed in this project, this image illustrates the overall topography and site characteristics of a typical heap leach pad in the Andes Mountains. Let us now review the steps for setting up our coupled seepage and stability analysis in GeoStudio. The first step in setting up a numerical analysis is to create the geometry. In this case, we will be using components from a geological model created in Leapfrog to generate the 3D domain. We will start by importing surfaces as background mesh that represent the topography and the contact between the heap leach pad and the underlying bedrock. We will then import this contact surface again and offset it by 1 meter from the original position to create a thin, 1 meter thick region representing the liner system. We will then create a rectangular prism by sketching a rectangle and extruding it vertically. Then we will use the imported background mesh to divide the domain. First, a surface must be fit to each of the 3 background meshes. Then each surface is used by the cut command to divide the rectangular prism into several solids. The top solid is deleted as it represents material above the ground surface. The remaining 3 solids represent the ore, liner system, and underlying bedrock. The final step for setting up the geometry is to imprint a plane on the ground surface that represents the pond elevation. This allows the pond boundary condition to be placed in the desired location. Once the geometry is complete, we can start to define the physics on the domain. I will start by setting up the 3D seepage analysis. This transient analysis will start with the water level at the ground surface such that the heap leach pad is fully saturated. Over time, water gradually drains from the system until steady-state conditions are reached, given the applied annual average infiltration rate. This analysis lasted 8,000 days in order to reach steady-state conditions. The material properties defined for the ore, liner system, and bedrock are all listed here. The ore used the saturated-unsaturated material model, with hydraulic function estimation routines producing the functions for volumetric water content and hydraulic conductivity over pore water pressure. The other materials used the saturated-only material model. A water flux boundary condition was applied to the top of the ore, illustrated by the dark red boundary in the image. The value associated with the water flux boundary represents an annual average infiltration of 1,250 millimeters. The potential seepage face option was selected so that seepage was allowed from the ore surface, thus allowing the ore to drain over time. No boundary conditions were applied to the domain sides, so these were ultimately no-flow boundaries. Finally, a total head of 2 meters was applied in the area of the downstream pond, representing the water surface elevation. The final step for setting up a 3D analysis is to generate the finite element mesh. In this project, a tetrahedral mesh pattern was used with average element lengths of 10 meters. Mesh constraints were used to decrease the mesh size for the thin region representing the liner and to increase the mesh size in the bedrock. Once the 3D seepage analysis is set up, we will move on to creating the stability analysis in SLOPE3D. We will use the Morgenstern-Price method. The pore water pressures in the 3D stability analysis can be defined using a piezometric surface, which we will review in the demonstration portion of this webinar, using the RU or B-bar methods similar to a 2D analysis, or by using pore water pressure conditions generated by a 3D finite element seepage analysis. We will use this final option such that stability is computed given the pore water pressure results at select times from the seepage analysis. These times do not really represent actual time, but variable pore water pressure conditions in the heap leach pad from saturated conditions to the long-term steady-state conditions given the annual average infiltration rate applied at the surface. The slip surfaces were defined using the Cuckoo natural search algorithm, which automatically searches the domain, or within the specified extents on the ground surface, to locate the sliding mass with the lowest factor of safety. Both ellipsoidal and spherical sliding mass shapes are considered. We will set the minimum slip surface volume to 1 million cubic meters to ensure that we are assessing the global stability of the heap leach pad. The ore and weak surface properties were defined with the Moore-Coulomb material model as presented here. The properties of the ore were taken from a previous study of the project site done by Rees et al., while the properties of the weak surface associated with the liner system were assumed. The friction angle of 21 degrees represents the friction angle of the ore decreased by a factor of 0.5. A weak surface will be used to define the position of the interface between the ore and the liner, to which these properties will be assigned. The bedrock used the impenetrable material model. Now that we have reviewed the steps for setting up our coupled 3D seepage and stability analysis, let us open GeoStudio to start working on the Heap Leach project. In GeoStudio, I have created a new project file using the metric units of computation. I will open the Define Project dialog to add the title Heap Leach Pad Analysis. The first step in setting up my numerical analysis is to create the geometry. To do so, I will first add a 3D geometry to my project file. The GeoStudio window now shows the 3D view. We will begin creating our 3D domain by importing background meshes representing various surfaces from the original Leapfrog model of the project site. This Leapfrog model has been shared with me via Central, Sequence cloud-based collaboration and tracking tool. GeoStudio can import various geometry items using its dynamic connection to Central. I will select the Import icon, go to Import Background Mesh from Central. A dialog opens allowing me to select the Central server, project, branch, and ID. On the list at the bottom, I can go to the surface mesh that I wish to import. I will start by importing the topography. When the topographic surface mesh appears in the 3D view, you will notice that it is on its side. This is because Leapfrog and GeoStudio use different coordinate systems. We can easily transform the coordinates using the Remap Axes portion of the Import Background Mesh window. Let us change the y-axis to -z and the z-axis to +y. I will also press the Adjust Base Point option so that my domain is closer to the origin. When pressing OK, I am prompted to save my transformation template. I will select Yes, as I wish to use the same transformation on the other items I import from the Leapfrog project. The imported background mesh appears in the corresponding section of the Geometry Explorer. I will change the name to Topography. Background mesh can also be imported as files if you do not have access to Central. I will import the contact surface representing the bottom of the Heap Leach pad by importing an OBJ file. Again, I will select the Import icon, go to Import Background Mesh from File. In the dialog, I will locate my surface file called Liner Bottom and press Open. In the Import Background Mesh window, I will select the background transformation template that we used for importing the previous surface mesh. Then under Insertion Point, I will change the Y value to 1 meter to move the surface up vertically by 1 meter. Because I changed the transformation, I am prompted to save this new transformation template when I press OK. I will rename this surface mesh Liner Bottom. I will now import the same surface mesh again and offset it by 1 meter to create the thin layer representing the liner and collection system at the bottom of the Heap Leach pad. I will start by using the background transformation template so it is located in the same position as the previously imported surface mesh. Then under Insertion Point, I will change the Y value to 2 meters. Because I changed the transformation, I can save this new transformation template again. I will rename the surface mesh Liner Top. If I zoom in, you can see that there is an offset between the two bottom surface meshes, as we desired. Now I will create the rectangular prism that will represent the extents of the model domain. To do this, I will right-click on the XZ plane and select Sketch 2D. I will draw a rectangle that is just within the extents of the surface meshes. I will then select Edit Plane and specify an offset of -12 meters. So this sketch sits on a horizontal plane at Z is equal to -12 meters. After pressing OK, I will rename this item in the design history, Domain Sketch. I will extrude the sketch to generate a rectangular prism by right-clicking on the sketch, selecting Extrude, and editing the default slice width to 200 meters. The generated solid appears in the 3D view when I press OK. For now, I will select the solid and turn off its visibility while I perform the next step. I will also change the name of the step to Domain Extrude. The next step is to fit surfaces to the background meshes that we imported. I will start with the topography. In the top toolbar, I will select the Fit Surface to Background Mesh option. In this dialog, I will change the surface resolution to 1, the flexibility to 0.8, and the Extend option to 0 meters. I can select the Show Deviation option to see how different the fitted surface is compared to the background mesh that was originally imported. In this case, we have a decent fit. After pressing OK, I will click on the Topography Background Mesh and will turn off its visibility. I will rename this step to Topography Fit Surface. Now I will do the same thing for the background mesh representing the top of the liner by going to Fit Surface to Background Mesh, selecting the background mesh that represents the top of the liner, and I will enter the same parameters as I did for the previous surface. After pressing OK, I will rename this step Liner Top Fit Surface. I will then turn the visibility of the liner top background mesh off. The final surface I need to fit is to the background mesh representing the bottom of the liner system. Again, I will go to Fit Surface to Background Mesh and enter the same parameters. After pressing OK, I will rename this step Liner Bottom Fit Surface. I will then turn off the visibility of the liner bottom background mesh. If I zoom in, you can now see the small offset between the two surfaces representing the top and bottom of the liner system. I will now turn the visibility of the solid back on. I will start by cutting the domain with the topographic surface. I will select the Cut command, and in the Bodies A input, I will select the surface representing the ground. Under Bodies B, I will select the solid, and then choose the Split Cut option from the top of the Cut dialog. After pressing OK, I can see that there are now two solids. I will rename this step Topography Cut. Then I will select the top solid, press the Delete Bodies command, ensure the solid is specified in the Bodies box, and press OK. This step will be renamed Topography Delete Body. I will now cut the domain with the surface representing the bottom of the liner. I will select the surface, then press the Cut command. I will ensure the solid representing the domain is under Bodies B, and toggle on the Split Cut option. After pressing OK, I will rename this step Liner Bottom Cut. I see multiple solids in the geometry list. I will merge all of the solids that do not represent the heap leach pad. By clicking through the solids, I see which solids I wish to merge. I will hold the Control key down and select these. Then I will press the Merge command. The solids all appear in the dialog. After pressing OK, I have two remaining solids. One for the heap leach pad and one for the underlying bedrock. I will now cut the domain with the surface representing the top of the liner system. I will select the surface, press the Cut command, and ensure the top solid is specified under Bodies B. Again, I will choose the Split Cut option and press OK. I will rename this step Liner Top Cut. The final step for setting up the geometry is to imprint the location of the downstream pond on the domain. This pond has a water level of 2 meters. I will start by right-clicking on the XY plane and select Sketch 2D. I will draw a box around the domain and press Edit Plane. In here, I will specify an offset of 2 meters to change the elevation of the sketch to 2 meters above the XY plane. After pressing OK, I will change the name of this step to Pond Sketch. I will now right-click on this step and select Make Bodies. Under the options, I will select Generate Surfaces. This generates a planar surface associated with my sketch. I will rename this step Pond Surface. I will now imprint the sketch on the ground surface. To do so, I will press the imprint icon in the top toolbar. Under Tools, I will select the newly generated surface. Under Arguments, I will ensure that I am selecting a face with the selection options on the right side of the GeoStudio window. Then I will select the ground surface. I will ensure the Remove Tools option is turned on so that the pond water level surface is deleted once the imprint command is complete. I will call this Pond Imprint. Our geometry is complete, so I will now start to set up the 3D seepage analysis. In the Define Project dialog, I will add a transient seepage analysis. Under the Physics tab, I will leave the default properties such that groundwater flow is occurring due to pressure and elevation differences. Under the Water tab, I will set the initial pore water pressure conditions to come from a piezometric surface. I will also increase my maximum number of iterations to 1000 and change my under relaxation criteria to assist with reaching a converged solution. Under the Time tab, I will set the duration of the analysis to 8,000 days with 5,000 steps. I will select the exponential option so that they exponentially increase in duration. I will save the steps every 100th step. Now that the project definition is complete, I can close this dialog. I will start by defining my initial pore water pressure conditions. I need to establish the piezometric surface. To do so, I can use the imported background mesh representing the topography to set the initial water table at the ground surface. To do so, I will go to Define, Piezometric Surface, and press the Add button to create a new one. In the dialog that opens, I will select the background mesh representing the topography and press OK. I now see this piezometric surface listed in the window. The same method is used to define a piezometric surface in a 3D stability analysis in order to establish the pore water pressure conditions. The next step is to define my material properties. In the Define Materials dialog, I see that there are 4 materials that were previously defined for me, though this analysis will only use 3: the ore, the liner system, and bedrock. As previously mentioned, the bedrock and liner system both use the saturated-only material model, as these regions are expected to remain saturated. The ore uses the saturated-unsaturated material model, where GeoStudio's built-in estimation methods were used to establish the functions for volumetric water content and hydraulic conductivity over pore water pressure. Once the materials are defined in this dialog, we can apply them to the 3D domain. I will ensure my solid selection is turned on in the selection preferences, and first select the ore and assign the corresponding material using the drop-down in the Properties portion of the 3D view. I will do the same for the solid representing the liner system, and then for the bedrock. My material definition for the seepage analysis is complete. The next step is to define the boundary conditions. In the Define Boundary Conditions dialog, there are 2 boundary conditions already defined. One representing the downstream pond elevation of 2 meters, and the other which represents an annual average infiltration rate of 1,250 millimeters. The annual average infiltration is specified as a water flux and includes the potential seepage face review option to allow water to seep out of the domain on the applied faces. After closing the dialog, I will ensure the face selection option is turned on and select the surface of the ore. In the Properties dialog, I will select the boundary association to be the annual average infiltration boundary condition. Then for the face representing the downstream pond, I will select the corresponding boundary condition. The final step for setting up our seepage analysis is to define the 3D mesh. I will refine the mesh in the liner region by selecting the corresponding solid, and in the Properties dialog, specifying that the element edge length is a length of 1 meter. For the bedrock, I will do the same, except I will specify that the element edge length is 20 meters. I will then press the Generate Mesh command in the top toolbar and specify that the edge length is 10 meters. You will notice that at the bottom of this dialog, I can specify the grid spacing for a 3D stability analysis. I will leave this as the default 9 meters. Once the mesh has generated, I can add locations to plot results at. I will select the location icon in the top toolbar. I can use one of 4 options for defining locations. I will select the polyline option and will add 2 points, one at an x of 140, y of 144.372, and z of 245. I will add another point at x equals 140, y equals 0, and z of 245. You can see that this creates a vertical line through the deepest portion of the heap leach pad. It's helpful to name the location so you know what it is when you go to create a graph in the results view. I could also create a location representing the top face of the heap leach pad. For example, if I wanted to assess flow across the surface, I would do so by selecting the geometry location type, ensuring the face selection preference is turned on, and selecting the top surface of the heap leach pad. Our seepage analysis definition is complete. I will now create the 3D slope stability analysis. I will go back to the Define Project dialog and add a SLOPE3D limit equilibrium stability analysis as the child of the transient seepage analysis. I will leave the default analysis type as Morgenstern price, as well as the half-sine side function. The pore water pressure conditions are automatically set as the results from the last step of the parent analysis. I could change this to all steps. However, since there are so many, I will select the initial time step only for now. Under the Slip Surfaces tab, I wish to use the Cuckoo Natural Search algorithm for locating the critical sliding mass. I will leave the default settings for the number of iterations and nests. Other than these settings, this method does not require any further definition. Finally, under the Convergence tab, I will change the minimum slip surface volume to 1 million cubic meters. My analysis definition is complete, so I will close this dialog. The materials are already specified on the domain. However, let us open the Define Materials dialog to review these. The ore uses the Moore-Coulomb material model with a unit weight of 20 kilonewtons per cubic meter and a friction angle of 38 degrees. For the stability analysis, both the liner system and bedrock materials use the impenetrable material model. That is because we wish to force the slip surfaces to the interface between the ore and the liner system. To do this, we will add a weak surface to this project and assign the weak layer material properties to this surface. The weak layer material also uses the Moore-Coulomb material model with the same properties as the ore, except for the friction angle, which was set to 21.3 degrees. To define the weak surface, I will go to Define, Weak Surface, and Add One, similar to how I defined the piezometric surface in the 3D seepage analysis. I will select the surface representing the top of the liner and press OK. I will then assign the weak layer material to this weak surface using the drop-down menu at the bottom of the window. The weak surface definition is now complete. This analysis is now ready to solve. Before doing so, I will add another stability analysis that uses the final pore water pressure conditions from the seepage analysis. Back in the Define Project dialog, I will clone the initial slope stability analysis and rename it. I will specify that the pore water pressure conditions come from the final time step in the parent analysis. Otherwise, I will leave the rest of the analysis properties the same. We would now solve these analyses and then interpret our results. However, for the sake of time, I will review the results in the following slides. As expected, water drained from the heap leach pad gradually over time, reaching the long-term steady-state conditions at around 8,000 days. The pore water pressure profile at the vertical polyline we previously defined in the mesh locations shows the sharp break in the results given the presence of the liner system with much lower hydraulic conductivity than the overlying ore. We can see the pore water pressures decreasing throughout the heap leach pad over time as the water drained from the system. However, under the long-term steady-state conditions, there is still a substantial saturated zone above the liner. It is important to check the convergence results, and in doing so, we can see that there are no convergence issues here. As water was allowed to drain from the domain, the pore water pressures decreased and the corresponding factor of safety increased. The graph shows the pore water pressure computed in the center of the heap leach pad just above the liner system. The range of pore water pressures here represents fully saturated conditions in the heap leach pad to the long-term steady-state conditions given an annual infiltration of 1,250 millimeters. Under fully saturated conditions, the factor of safety is below 1. The sliding mass comprises the front corner of the heap leach pad and follows the weak layer, as shown in this graphic. This represents a large-scale translational failure controlled by the liner system. Under the long-term conditions, the factor of safety increased to approximately 1.23. As expected, the sliding mass followed the weak layer. The sliding mass shape is slightly different but has a similar position and sliding direction as the saturated conditions. The top view of the results shows the similarity between the sliding mass position as well as the sliding direction. However, even though there are similarities between the stability results and the failure mechanism, the influence of pore water pressures is still significant. The factor of safety increased by 70% from saturated to the long-term steady-state conditions. Thus, stability does significantly change as water drains from the domain. It is important to note that we wouldn't expect the heap leach pad to be at the fully saturated state, as shown on the left. Typically, we would expect the long-term conditions to be present at this site. However, weather extremes, including prolonged heavy rainfall events, could lead to an increase in the volume of water stored in the heap leach pad and corresponding pore water pressures. This would cause a drop in the factor of safety. Since the factor of safety is not significantly greater than 1, under the long-term conditions, we would expect that the heap leach pad might experience short periods of instability associated with the pore water pressure conditions caused by heavy rainfall events. Further analysis is required to determine the amount of precipitation required to cause these conditions. This concludes our demonstration of a 3D seepage and stability analysis of a heap leach pad in GeoStudio. Overall, we determined that the critical failure mechanism was large-scale translational failure controlled by the weak surface associated with the liner system. Nevertheless, the pore water pressures had a significant impact on the stability results, with a long-term factor of safety just above 1.2. Resources related to this webinar are available online. An online course, GeoStudio 3D Basics, is available in the Sequent Learning Center. For more information on SLOPE3D and its fundamentals, please see our newly updated Slope Stability Modeling with GeoStudio manual. A paper was also presented at the Canadian Geotechnical Conference this year entitled 3D Seepage and Slope Stability Assessment of a Heap Leach Pad. This paper is available upon request. To learn more about GeoStudio in general, there are many tutorial videos, example files, product manuals, and past webinars available on the GeoStudio website. We've now reached the end of this GeoStudio Tech Talk. A recording of the webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.